Welcome to Data Analysis 2. And as Olya already mentioned, this is obviously the second webinar, and we have a webinar 1. And yeah, check that out, and that will be the more basic concepts there. And we have now here a few new things we want to talk about, which are imputation, OPLS-DA, WGCNA, and power analysis. And just a heads up, imputation is obviously that you're handling missing data. OPLS-DA is a multivariate technique to enhance statistical power. WGCNA is also a multivariate technique to enhance power, but it actually has the benefit of constructing meaningful modules. And then if that doesn't all help, you can do power analysis and determine the adequate number of replicates you should have had to get a proper result. Okay, so imputation first, and that is, as said, the effective handling of missing data. And yeah, you probably know if you do lipidomics analysis and especially untargeted, you have missing values, and that doesn't have to be a problem. So if you, for example, have missing values and do a univariate analysis and you have a set where you have more and a set where you have less replicates, you can still do the analysis. That doesn't stop you anything from, and usually that's also what people would say that's more rigorous, that's preferred. But some methods actually need the missing values to be imputed, so they can't handle the missing values themselves. And the one that comes to mind usually is the principal component analysis. And you could also argue that in some cases, strong effects are undetected because you don't have sufficient power. Let's say in this case here, down here, you would lose some values, and that's a really strong effect, but yeah, you're missing power here. That can help. This is obviously a case where you might want to think about if you really want to base all your findings on imputed values. But yeah, nevertheless, mostly you would rather deal with models that have to be, well, like a PCA, then you need to impute. Important to understand here is that there is different types of missingness. First of all, there is missing completely at random. This is the left case, and here what is meant is that a value is simply missing by chance. If it's up here or down here, you roll the dice and that's missing. And then there is missing not at random, and in our case, that would be lipids that are missing, for example, because they're below the limit of detection. So down here, it's missing data that's not dependent on any information that you have. And then there's another case, the missing at random, which is missing data depending on available information, but we don't go there now. If you do have these two concepts, that's perfectly fine. It's important to understand that it's actually nearly impossible to determine the missingness in practice. So if you just have a missing value and you can't tell if it's one or the other kind. So in the first part, I'm going to tell you a little bit about our experience with different methods of imputation. And we just got this published in proteomics. So if you want the full-fledged paper version of what I'm going to tell you, you can also have a look there. But let's first, so what kind of methods do we have? If we have, let's say, a lipid, which has certain values here and is distributed across multiple samples here, we now assume, okay, you have one value missing. So what can we do? So one thing is simply we impute by zeros, and that's very relatable. If you look at your data, this one is missing, it has not been measured, it's probably not there. Let's replace it with 0. This works in a lot of situations. It's, however, a very strong assumption, and you might, if you experiment with different PCAs, you might see that this has a strong effect, for example, in your PCA plot, score plot. But also one problem that you also have here is that all your missing values are replaced with the same value, which is kind of unnatural, and and doesn't have the natural variation you usually have for your values. A less harsh variation of that is the half minimum. So you simply take all the lipids that you're having and replace with and find the lowest one, and then divide this value by half, and that's your value. So this is a different version of the zero implementation, but you basically say, okay, we actually give it half of the lowest value that is found in that lipid. Other values that you usually do is other algorithms that you usually do is median or mean imputation. And that's, of course, very relatable also, that you would say all values should cluster around the mean. So the most likely is the mean, and we replace our values with the mean value. Median is just a little bit more stable against outliers, but basically the same thing. So then there is a set of models that we recently got fond of, which is k-nearest neighbor methods that are either based on correlation or even truncated distributions. And what does that mean? It's basically that you have a lipid that you want to impute, and you look for another lipid or multiple of those which are very highly correlated. And then you would say, okay, this value is below here, this is below here, this is below here. So this one is probably also around here. The correlation version of this is based then on a normal distribution, and the truncated version is based on a truncated normal distribution where you assume that some values at the lower end are missing. And we got this from the paper you see below. That's Shah et al. And the last version here is random forest, and that here you actually use not one, you use possibly all lipids in your lipidome to determine what is the value you should expect here. And that also works, and works usually very well. And however, it's also computationally much more intense. So what we did now is to use all these methods, and in a first approach did some simulations. So we simulated here the missing completely at random. So this is where you just toss a dice and some value disappears. And just had a look how well are these behaving. And what you notice is that median and mean actually perform quite well. They center around 0. So there's random forest with a bit of narrow distribution. 0 and half minimum are far off. By definition, 0 is like 100% off. And the half minimum is also quite off. This is shown at a log normal distribution, but especially as a correlation of these simulated lipids of 0.8. And then situation looks quite different if you go for the missing not at random. So here first 0 and half minimum look much closer than before, but median and mean are quite off. Random forest also isn't better, but still is not as good as the correlation-based or the nearest neighbor-based algorithms that either are with correlation or even truncated. And the truncated, obviously, this is the case it has been designed for, is much better. So as I said, this is as a correlation value of 0.8. So these things obviously depend on correlation. So if you look at the completely at random, missing a completely at random case, there is not much dependency on the correlation. However, if you look at the missing not at random, there is a strong effect of the correlation of the lipid that you're imputing with. And if one looks, then one say like at 0.6 about, this is a good value where you should switch over to either the correlation or the truncated version via imputing. Okay, but what are typical values that you find in your lipidome? So here we actually put the highest, the second highest, and the third highest lipid. What that means is here is a histogram of every lipid for every lipid with the correlating value, which is the value which is the highest correlating lipid. So, and you find that here with the medium of 0.78, half of the lipids are higher than 0.78, and the other half is lower. So usually the first lipid is fairly high correlating, and that's why these methods are valid. And the second and the third are also similarly high. So this is for human plasma, and we also published a mouse atlas. We did it in that data set, then things are even higher. So if you do the same in real data sets, you see it's a bit more nuanced. Random forest is also actually quite good here in plasma in the completely at random case, and here in the missing not at random. It's also not too bad, but these correlation-based or nearest neighbor-based algorithms are doing quite well. And the same in the mouse case, with just a bit more spread here. So summary is, or to take away what you should notice is that these methods are not bad per se. They actually work well in one or the other scenario. Like 0 or at beta half minimum works actually quite good in the missing not at random case. Mean, median work well at the missing completely at random case. Random forest is also quite good in both cases, but really shine to these two, where you have where they work very well in the missing not at random, but also very well in the completely at random case. Good, so that's our takeaway. Look at your imputation and see if you can use something more sophisticated than zero imputation in particular. Good. Next, we have multivariate methods. And here, first of all, what is that? What is a multivariate? Yeah, you can contrast this to a univariate method, which simply means that you are testing every lipid individually. So for every lipid, you do a statistical test, and hence you testing that one dimension, that one lipid. And because you do so many of these tests, you obviously have to do multiple testing correction. That means that you adjust your p-values for the fact that you could find something by chance just because you do so many tests. And the challenge is obviously one, either you get, like in this case, a lot of significant lipids and have to find out what you do with this. That is then an enrichment analysis or other methods. Or you have little significant lipids after multiple correction because, yeah, you have to correct so much. And the answer for this is then usually multivariate methods. And as I said, I tell you two of them. And the example we're going to use is this knockout of ceramide synthase 2. So you have a control and ceramide synthase 2 knockout, and this just gives very nice specific phenotypes, which means that you have a loss of long chain sphingolipids, so sphingomyelin, hexoceramides, and ceramides in our case, where these long chain around 42, 40 are reduced, and you have an increase in the shorter chain sphingolipids, which have about 34 carbon atoms. So OPLS-DA is an orthogonal partial least square discriminative analysis. And partial least square is a model that works with a dimension reduction technique. Discriminant analysis means that you're trying to separate two cohorts. And orthogonal is here a special case which tries to put all the variance between the cohorts on the first principal component, or component 1 in this case. And yeah, it's a dimension reduction technique. And what does that mean? That means that you usually have in your lipidome hundreds of dimensions because you have hundreds of lipids, and you try to reduce the dimension to a few. And the example I come up with is much easier. Think of something like a three-dimensional object, let's take this pen here, or pencil, and that has a clip, and you want to know if the pen has a clip or not. And now you have this three-dimensional, so a Lipidomics 100-dimensional object, and you try to make a projection in a two-dimensional space. So that's obviously straightforward. You just cast a shadow. But there's multiple ways you can do this shadow casting. And if you look at a principal component analysis, which is an unsupervised method, it would just go and say, what is the highest variation in your data? And put this variation, so the longest shadow, along the first principal component. And then look for the second perpendicular components with the highest variation, in this case, that, and put that in the next. And so you go on for multiple principal components. And the fact here is you're going to see at the first principal component, of course, the highest variation, but not like in our case here, this doesn't reflect our question. It's not showing anything about the clip or not that you only find in the second principal component, and you might not find it in any one contrasted such that you can make a real statement. In the case of the OPLS-DA, you would now have a supervised model that tries to really distinguish, let's say, molecules in the pen by molecules in the clip, and would force this separation on the first component. And here you would have everything that separates pen from clip. So far, my little example. So here we have it again, like from the last seminar. There is this PCA, a dimensional reduction technique, where you get a score plot, where you have your samples and you have a loadings plot that tells you what the amount of or what the contribution is to of the lipids to the individual components. So if you now go for the OPLS-DA, you have a similar score plot, and you would have now two cohorts that you try to separate. And on the one hand, you would try to force this separation. And if it works, you have all of the one cohort on one side, and on the other side, you would have the other cohort. And hopefully no overlaps. This is kind of the score plot. And then you would be obviously interested what makes the difference. So you can also do a loadings plot like before, but you can also do a S-plot, as we've shown here, that is showing on the x-axis, it shows the magnitudes. This is the absolute covariance values that shows how the contribution to the separation. So the higher values are on the x-axis, the higher the contribution to the separation by the model. And on the y-axis, you have the reliability, the correlation that tells you how stable this individual value is. And then it depends. It's actually then it's a bit arbitrary where you draw the lines. We have actually chosen that you be showing these plots the 90% quantile of the absolute value. So you might have values up here and values down here. But that is then basically your choice, what you find interesting and which lipids are good for the separation. So if you have a separation, you obviously think you're done. In this case, that's not the case, because this model could also come by chance. You could actually have this separation, and this would not be stable. So what you do is a permutation plot. So you simply swap out labels, put this over here and this there, and then see if you get a similar or a better or a worse result. And so we do this permutation plot, and what you see in the x-axis is how similar the labels are to the one you started out with. So here's everything you did the model. Here you actually replaced 1, 2, 3, and so on of the labels. And then you do this again, and you see how well your model performs. And if the model performs worse than the model you started out with, your real model, and this happens enough time, you can assign this a p-value and say, this is a good model, this is a stable model, has some significance. However, if the points would end up above or at the same level, you would say, okay, this model is not stable enough. We should take this with a few grains of salt. So, summary, OPLS-DA effectively separates cohorts. It's robust to multicollinearity. I haven't mentioned this yet, but in lipidomics, you have the fact that you have high correlation means that a lot of lipids point in the same direction, and then a lot of models get confused. OPLS-DA, by doing the dimension reduction, can effectively deal with this multicollinearity, which is good for lipids. OPLS-DA separates the predictive variation, so what is actually in your lipidome, distinguishing between the two cohorts from the variation that is within the cohorts, so intra-class here. And you have visualization and interpretation techniques that you can use. So that was the first multivariate technique. The second is a WGCNA. And here we have it as weighted correlation network analysis. And as I said, it's also a multivariate strategy, but this time you also get meaningful modules. What WGCNA means, you can get different meanings according to where you ask and when you ask, because it was originally developed as a weighted gene co-expression network analysis, but then actually was acknowledged that it's also can be used for other things like in omics, and that's why it's often referred to as weighted correlation network analysis. Again, it tries to overcome the multiple testing problem and makes also, hopefully, biologically relevant molecules. And what you see a lot is this plot here, which is from one of the author's publications, which basically says these are the steps you need to do. First, you need to construct a co-expression or correlation network. You need to identify the modules. You need to relate them with the information you care for, like in our case, cohort versus control versus knockout. And then you need to look into these modules and see if you find something interesting, and find also the key drivers of this network. So I'm not going to go into all the intricacies of most of these steps, because there is a lot to unpack, and there's a lot to set, and then it's also that some of these modules are created and later fused. So I will actually stay with a high-level explanation of what we're doing here. And first is to understand is you will simply construct separate models, which always are called according to the color. So in our case, we had about 650, let's say, modules and lipids, and you construct about 7 modules for that. And that you do based on correlation. So these two triglycerides are nicely correlated. They would end up in one model and one module. And this cholesterol ester here would be probably ending up in a different module because it behaves very different across the samples. So, and then you would calculate something which is called module eigenvalues and correlate them with the outcome. And by this, you would get a result which would tell you that there should be a pink over here module that has a very high correlation with the external information that is control versus the knockout that you're looking for, and also has a very strong p-value. And there might be another one which is not significant, but that has a negative correlation. And so you could end up with multiple of these modules that are interesting. And you could also do this for multiple tests at the same time also. So you have a module, and that is actually nice because that tells you, okay, there might be a common functional process behind all these lipids. That's why they do correlate all across the samples. And then you would have to look what you're actually finding here. And as you see, there's some sphingolipids and other lipids all in here that you found. This is your group. And one thing you could do is you look into that module and say, okay, how strong do these individual lipids, how much do they contribute to this pink module? And you can have a look. And what you find again are these long chain sphingolipids that you've seen before. You could simply take all these lipids and do a ranked or a normal enrichment analysis, and you would find that you're finding sphingolipids, you find the total length enriched, you find ceramides, phosphatidylserines, and hexosylceramides enriched. So basically what we put in, and already know that in this case, this is what you're looking for. So hopefully with this, you would find modules in your data that have biological meaning, that are then easier to interpret than just a whole huge number of significant lipids, which we also found in here. Okay, last but not least, if that all doesn't work, how about to the drawing board, and can we actually increase, let's say, the power of the univariate analysis? And of course, you're trying to find the adequate number of replicates for your analysis that you're doing. And there's a few things you need to understand, or a few definitions you need to have. And one is simply statistical power. And statistical power is the probability that a statistical test will correctly reject a null hypothesis. So in other words, if there is really a difference, will you find a significant p-value? And if you're on the simulation side of things, you would actually say this relates to how many times do you find a significant result compared that you don't find a significant result if you do this, if you simulate this test multiple times. And obviously, if you're always doing the same test, so I've sampled here from two different distributions of this lipid, and say you increase simply n, obviously you higher the n, the smaller the p-value, the more often you find a significant result, or the lower will be the p-value you achieve. So better is like, more is always better in this case, but yeah, what can you get away with is the question. And another thing you need to look at here is the effect size, which is simply a measure of how big the difference is between the two means that you're having. So I just go back once, how big is the difference between the values in one cohort you're having versus the other one. But this is not necessarily all you need to know. It's also important how much variation is there. So one way of dealing with this is called OPLS-DA, which is a measure that takes into account the two means, the difference between the two means, and the measure of the standard deviation. And these can be simply values, but they also have been coined into classes. So a OPLS-DA value below 0.2 is then termed negligible, and then this one here would be small, medium, large, or even huge. That has been extended at some point. So if you look at your lipidomes, you might find different distribution of these effect sizes. Some might be, this is an example here for being negligible, so really small. There's a very small difference, and the distributions look very much alike. And middle, you already see that one curve is slightly different, and huge is already this, that the means are clearly separated. If you have a OPLS-DA, or you have the mean and multiple replicates, it's actually quite easy to calculate. You can simply go online or go into, let's say, R, a statistical programming language, and simply say, okay, I have a coincidence D of 0.6. I want the power of 0.8. So 80% of the time I want to see a significant result, and it actually gives you straightforward the result, what you need. This is in the case of one lipid. You can do that very easily yourself. If you want to do Bonferroni correction, that means you simply multiply by the number of tests you do. That you can also be easily done, because then you simply multiply this by, let's say, 500 or 700 lipids that you're having. Usually that's too conservative for the lipidomics point of view, and that's why we developed our own simulation scenario for this. And this is this one. And I'll just quickly go with you what we do here. So what you're always going to need is you will need some pilot values. Some kind of measurement that you have before, minimum, let's say 3, that you can say, okay, this is what the distribution of my lipids and what the effect size is that I expect. From this, you can actually estimate the distribution. Doesn't have to be a normal distribution. And from that, you can then simply sample. And from the sampling, you can make a statistical test. This then you don't only do for your one lipid, you actually do it also for lipid 2, 3, and all the lipids in your lipidome. You get all the p-values, you put them into a multiple testing adjustment method, let's say Benjamin Hochberg or something, and then you get your adjusted p-values, which have less significant than before. And then when you have this, you have one of the points that says, okay, in this case, I found a statistical significant test or not in your ratio of powers. So what you need to do is you need to repeat this a lot of times, 100 or 500 times, and thereby get a ratio of how many times have you found a non-significant or a significant test outcome. And from that, you can actually then say, okay, because I only found, let's say, 20 of 100, I have now 20% power in the case for this one lipid that I drew 5 replicates. But you can obviously do that also for lipid 2 and 3, and then replicate this for not only the time when you have 5 replicates, but also 1, 2, 3, 10, 50, and so on. And from this, you will actually then get curves like this. So in this one case, which was a plasma lipidome, you would say if you have a huge difference, of course, after a few replicates, you jump to 100%, and you will definitely see a significant results if you do this, let's say more than 3, 4, 5 times. 3 is probably not, but let's say 5 times. In case lipids are very similar, if that are the lipids you're particularly interested in, yeah, let's say you do a plasma screen, you will need probably more replicates in this kind of scenario to see your difference. These things can obviously have to be adjusted then according to your needs, and say, okay, this is what you what your scenario is, what your test is, and so on. And then obviously you could look into individual lipids, but you could also say, okay, how many of my lipids have a 30% power? And if you want 50% of your lipids have 30% power, you might need about, say, 15. But if you want to have this for 90% power, you might need a way higher number. Good. So that's a setup that one could use for doing power analysis for a lipidomic analysis and find out how many lipids you need. So in summary, what I try to tell you is, a few new tools to play with. There's imputation, where you, if you have missing values, you can impute them. If you don't get it along with univariate analysis because your power is too low, you can increase that by multivariate techniques that either are working with dimensional reduction, like a PCA, or they also construct meaningful modules on the way, like the WGCNA. And if that doesn't work, yeah, then probably you might need to do the same thing again with a higher power by increasing the number of samples that you're having.